Okay, so our part 1 of 5.2 ended off with this sum, and I just wanted to write down one more thing that goes along with the Riemann sum. Again, CK is a midpoint of the quote unquote kth interval. So for the first interval, you would find f of C1, which is that height. You would multiply that by the first change in x, delta x1, which is b minus a over n. And then you would add that to the second rectangle, which would be f evaluated at C2, which is the midpoint of the second interval, times the base of that rectangle, which would be delta x2. But again, these are all going to be the same because of the way that we split them up, so on and so forth. So I just wanted to clarify that. So that's what is known as the Riemann sum, the sum of n number of rectangles, okay? And then that gets us approximation for the area under some curve between that curve and the x-axis. Now, what I need to do, so that basically is a bunch of little geometry problems. Base times height plus 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 base times height. And notice I used MRAM to do those. That's what 5.1 was all about. Okay, so we need to now graduate or mature to the calculus version. The calculus version is what allows us to get an exact answer. But the only way I'm going to get an exact answer is if I get rid of all of those little teeny bits of error. And in the video we watched today in class, we found it had something to do with a limit. Okay, so here's what's going to happen. I'm basically going to take that Riemann sum. So again, I begin with k is being summed from 1 to n, so I have n number of rectangles. I have a finite number of rectangles. F of ck is the height of each rectangle, where ck would be the midpoint. So we're using the midpoints to determine those heights. Delta xk is the change in x. So this little delta stands for change in. And you're probably wondering why I'm calling it delta. That's another Greek letter. So whenever you hear someone say it's all Greek to me, well, in calculus it literally is. So this is their letter for our d. Delta, d, kind of the same thing. So this is delta x is the change in x. And that's referring to the base of each rectangle. So if I take this simple geometry problem, which is adding up base times height, base times height, base times height, n times, and I now allow that n, the number of rectangles, to approach infinity, that's calculus. There is our calculus spin. What that will do is it will basically find the exact area. That is no longer an approximation. That is exactly how much area is between that curve and the x-axis. And so there is notation that goes along with that exact area. And instead of this capital sigma from Greek, we use kind of this stretched out s, is an integral sign, again standing for a sum. But it's a little different. This is a finite sum. This is an infinite sum. This is the result of taking the limit of this as n, the number of rectangles, approaches infinity. So you have the integral from a to b, so that's the left endpoint to the right endpoint, and you got to go in order, of f of x, which is this curve. Notice it kind of takes place of f of ck, and then dx. That's a differential, the kind of differential we learned back in 4.5. These are one and the same. That is the leap. This here is the calculus. This here was the geometry. The limit, as n went to infinity, is what caused this to become that. And this is the exact amount of area between f of x and the x-axis. Now, we won't learn how to do this by hand until 5.3. So you're going to have to hold on. What you're learning today is the notation and what it means. Today is all about concept. Okay, so this is a definite integral. It's the limit as the number of rectangles approaches infinity, and you're summing up infinite amount of rectangles. If that limit exists, we say that f is integrable. We are able to find the integral if that limit exists. Okay, so this is the more common limit you will see. I need to also point out some notation in our book, as well as I've seen this same notation used on other AP tests. So another concept we need to consider is, as the number of rectangles is approaching infinity. So taking that limit as n goes to infinity, we have to think about what that's doing to the change in x. We're adding more and more and more and more rectangles in here. We're squeezing infinitely number of rectangles in here. That's going to force the change in x to approach 0, because here was our change in x. It was basically the distance between a and b split up into n subintervals. And if you take the limit of that as n goes to infinity, here, let me squeeze that in there. Take the limit of this as n goes to infinity, well, you get 0. Because you have some constant number divided by a really large number that keeps growing. This turns into a very small value and it heads toward 0. So it turns out that the base of each rectangle, or the distance between x, that thickness of each rectangle, is getting squeezed in because the number of rectangles is increasing, causing the base or the width, whatever you want to call it, the thickness, to shrink down and eventually approach 0. So in the book, instead of using intervals or subintervals, they like to use the word partition. So P stands for partition, and that's just basically the act of splitting the interval from A to B into subintervals. They have this notation with these double lines and the letter P, and that is notation for, they call it the norm, and it basically means the largest subinterval. Because in the book, they don't assume that we split up the intervals evenly, which is what we will do, but they're saying, okay, let's say you didn't do that. Take your largest subinterval and take the limit as that largest subinterval, approaches 0. So they're taking their largest subinterval and making it approach 0. That will force all the other subintervals, because this one has to be the largest. So if the largest one is approaching 0, that forces all the other ones to get smaller as well. And so we have f of ck times delta xk. So if you force your subintervals to approach 0, you're basically forcing the number of rectangles to approach infinity. So this is another notation that means the same thing. So this notation is equivalent to the limit as n was approaching infinity. So having the subintervals approach 0 is the same thing as forcing the number of rectangles to approach infinity. And that's the same thing as a definite integral. So these three are one and the same. This is book notation, and I have seen it on some AP tests, where this double lines with the P means the largest subinterval is approaching 0, which means the number of rectangles must be increasing. So it's the same thing as saying, okay, the number of rectangles are approaching infinity. It means exactly the same. And so that's basically what we call a definite integral. It's finding a finite area between a curve and the x-axis. Okay, so on the next video, we will move on to page 2.